Hello, today I'm going to explain how magnetic levitation mechanism works, and then I'm going to explain how levitate plants works, and then I'm going to explain how we can simulate magnetic levitation with MATLAB Simscape tools. What is magnetic levitation? Suppose we have two permanent magnets inside a tube with opposite direction, and they push each other, and if we push upper permanent magnet, it's pull down and increase the force. If we change one of the permanent magnet to a winding coil, we can produce a magnetic flux inside the tube, and we can change the position of permanent magnet. One example of a user of this is moonwalker shoe. Moonwalker shoes, when you are walking on the street, you feel you are walking on the moon surface. Inside the shoes, it has two layers of permanent magnet with opposite direction. It puts your foot and pull your foot up. Another fun idea, we can build a permanent magnetic gun. Permanent magnetic gun has an array of permanent magnet and a small beginning of the tube is a small electromagnetic coil. We can accelerate a metal ball inside the tube with this mechanism. Another example is levitating train or MATLAB. MATLAB is levitate with opposite direction of two or four permanent magnets. And propulsion mechanism is like a linear brushless motor. Another mechanism is spin stabilized magnetic levitation. It comes if we spin top of the surface, and the mechanism looks like this picture. The permanent magnet produces force in z-axis against the gravity, and gyroscopic effect will stabilize the spinning top toy. Levitating plants mechanism. Suppose we want to levitate plants in air. It has a mechanism look like this. It has two permanent magnets, one for planet and one in bottom surface, and for electromagnetic coil for a stabilized upper permanent magnet, just for stabilize. And the height of the upper permanent magnet will it's with bottom permanent magnet. I draw a model in the SolidWorks software. We can see for 5 permanent magnets for bottom and 1 top in upper side. In the upper side, the direction of permanent magnet is same as bottom permanent magnet. If you see the direction of magnetic flux, it's we can see its opposite direction in middle of the part. You should use the same direction to levitate. And for electromagnetic coil, for stabilize in X and Y axis and Z axis with permanent magnet will be stabilized. As you see, if upper permanent magnet wants to tilt, the electromagnetic coil will be produced against the upper direction magnet. As you see, it's a control loop. In the control loop, we have a PID controller, electromagnetic coil driver, electromagnetic coil dynamics, and Hall effect sensor. We want to stabilize X and Y magnetic flux. We have 2 options for permanent magnets: neodymium magnet and ferrite magnet. Neodymium magnet has grade N32 and 52. It's 1.1 remanence Tesla factor to 1.49 Tesla factor for magnets. It's good to use M45 or M40 for this project, or you can use the ferrite magnet. It's 3 or 4 times weaker than neodymium magnet. We should use a huge permanent magnet for this project. We want the actuator we use for cross-connected actuator. We can calculate the inductance with this formula. We want mean radius of winding and number of turns. In this project, we need to measure magnetic flux. We can use the Hall effect sensor. Hall effect sensor measure the magnetic flux applied perpendicular to its surface. We can use Hall effect sensor in 2 modes. One is constant current driver. We can supply Hall effect sensor at the pin 1 and 3 with constant current or constant voltage. Magnetic flux is linearly related to output voltage, as you see in the right diagram. Constant current has changed the output voltage with change of ambient temperature, and we can use this sensor as a temperature sensor. But voltage constant driver mode is it's constant, produce constant output or change of temperature. We want to simulate of levitating planes. We show the control loop. We want to simulate the electromagnetic coil driver with MATLAB, Simulink, Simscape, and Virtuos software. Inside the electromagnetic coil driver, the microcontroller like STM32 AVR that can produce PWM signal. PWM signal for drive of coil needs to be a higher level input for coil, like 12 volt or 24 volt to drive the coil. If we directly input coil with PWM signal, it's converted to a buzzer and keep produce sound because it's very look like a buzzer mechanism. As we can use PWM to analog signal to solve this problem. For producing analog signal, we need to RC low pass filter. Can use RC low pass filter. I used 500 microfarad capacitor and 100 Hz cutoff frequency. With this formula, we reach the 3.18 ohm for resistor. I'm going to MATLAB software. I built this project at Simscape MATLAB Simulink. We have a solver for solve this physical simulation. We have DC voltage source to input to set duty cycle of our PWM signal. We have controlled PWM voltage. Inside the PWM control voltage, we should get PWM, should set up PWM frequency. Normally microcontroller and Arduino, they have 490 Hz frequency. For PWM signal, we can change to other frequency inside microcontroller, and or you can use this frequency. I use this for 490 Hz. Output voltage is 5 volt level as the microcontroller output, or we can use 3.3 volt as output. We have H bridge here. We want to produce 24 volt PWM signal with output power supply to power up our coil. We have low pass filter here. We have two low pass filter here because we have two direction. We want to drive coil minus 24 volt and 24 volt with two direction. We have two voltage sensor. Our resistor for about 3.18, I choose 4 ohm and 500 microfarad as the formula. If we run the Simulink, We set the voltage at 1 volt. It means we set duty cycle at 20% from 5 volt. If we see our signal will increase with PWM signal with 20% duty cycle, and with PWM at 490 Hz frequency. And the rising time is about 10 milliseconds, about 100 Hz. It's about cutoff frequency. The voltage is about 10 or 11 volts. If we increase the duty cycle like 2.5 volt, it means 50% duty cycle, you can see it's increased the voltage. We built an analog driver for our coil. It's same about a millisecond rise time. If we put it 100 duty cycle, we can see a small signal output because we have a constant 5 volt input. It's not ideal circuit because we have a resistor in our circuits. Waste our energy inside and convert into heat. We can use another circuit to filter low pass filter. We can use op-amp for low pass filter signal. As you see, we have a non-inverting op-amp circuit. Simple equation: frequency cutoff. We choose a 100 Hz and 1.66 for gain desired. As you see, 1 kilo ohm for R, 1.59 microfarad for capacitor, R2 and R1. If I change it to this filter with op-amp, we can set the voltage level. It's 100% duty cycle. It's about 24 volt with it's about 10 millisecond rise time. If we change, we can change it to 0.5 volt, and we can see the output. The output level voltage is same as 100%, but we can see we can use the op-amp as the digital to analog converter driver. It's just change the rising time. You can see it's change rise time about 20 milliseconds. Change the rising time, not output level. We can use this circuit. We have another option. We can use the LTC 2644 and DAC of analog devices. We can put the PWM input into channel and output analog signal. Inside the IC, it's PWM to binary conversion and then digital to analog converter produce the analog signal. As you see in the right diagram, we can see the smooth diagram for driving over coil. In about 0 duty cycle, it's a smooth signal. In 50% duty cycle, it's higher level voltage, and in about 90% duty cycle, it's higher level voltage, a small higher level voltage with very small rising time. You can use this driver to drive this project. Thanks for watching my video.